Hello everyone and welcome to the battery simulation workshop for beginners. My name is Sarah Reb. I am a synthetic chemist and I worked in the catalytic field for my PhD, and now I work for the Math to Market since August this year. As I'm also a newcomer in battery simulation, I have the experienced electrochemistry team in my bag, namely Ilona Klatt, who is the team leader, Fabian Biebel, who is the developer, Janine Hilden and Matthias Fingerle, who do a lot of project work, and Sven Linden, who's also developer in several fields, but also the electrochemistry. And in the next slide, I show you the whole Math to Market team, and I show you the persons I told you about. Here's Matthias, here's Ilona, here's myself, who's not looking at the camera, here's Sven, here's Janine, and here's Fabian. As GeoDict is a big box full of tools, I want you to show those who are important for the battery simulation. To import the data, you need the import GeoVolume. To create new cranes for a digital twin or something, you need a crane geo. To make the surface calculations and the porosity, you need the Pore and the GeoDict. You need for flow through the cranes of the ions, you need the GeoDict, and in the end, for the battery simulation, you need the BatteryDict. The workshop consists of 3 parts of about half an hour. After each of these parts, we'll have a 10-minute break. So during these breaks, you can either ask a question or grab a coffee or eat something. But of course, you can simply take a break. In the first part, we'll start with importing the 3D scan data. In our case, it is a micro CT scan, but of course the import is also working with other 3D image scans like a FIB-SEM data or something else. In the next step, we are going to visualize this tomography data in GeoDict, and we are going to make the segmentation. And after doing the segmentation, so that means we assign each pixel or each voxel to a fixed material ID, we will analyze the pore space, and then we'll calculate also the pore size distribution. Those are several ways of defining the pore size distribution. In the end, which one is correct depends on your application. The same is true for the tortuosity that we will observe in part 2 after a 10 minutes break. There are several ways also to define the tortuosity, and here also the best way is to check your application and then to find it the right way. We are going to present you the most common one for battery simulation. Then in the third part, we have a new feature. It's charge half cell. And we're going to work with this feature that allows you to make a charging simulation directly from the cathode material. So with this feature, you can speed up your mechanism to test new materials, and then we'll discuss those results and also learn how to build a full battery and run the charging process on this one. We will start our training with the import of the data, but which data or which material are we actually looking at? The data we have is from the ETH in Zurich. It is a NMC cathode material. And if you want to know more about this dataset, you can refer to the publication of Ebner et al. The dataset is also publicly available, and you can download it from the website of the ETH. When we now go on GeoDict, the first thing we do is to check this folder, because here all the data GeoDict is going to write will be saved. When there's the My First GeoDict project, that's normally the default folder. And you click on Select Folder, and now please select the handout folder I gave to you and go to the project folder that is empty and exactly for this purpose. You select it, and the next thing we are going to do is to check that the module import GeoVolume is open. If it's not open, you go on import and you select the module. The next thing, you go on browse and you go back to the import folder. The first one is this. In this folder there is the ETH NMC cathode folder where the microCT data are laid. Those are PNGs. You select just one of them, that's enough. You click on open and now you have the small window that opens where you check that the import all files in folder checkmarked is done and that the voxel length of 0.37, there's a 0 missing, is written inside. The voxel length is the resolution of the data you got. Then you click on image processing and you wait until GeoDict is doing its work. And it can need maybe some seconds. You just wait a little bit. And then you should remark that a new window is open. You see it here blank. This is the 2D scan view. From the X direction, you can slice here easily. You can also change the direction you view. From the Z direction, for example, it looks the same. From the Y direction, it should be something else. No. Here's the Z direction. That's the big size. And you can go also on 3D. That needs a short time to render. And then it's going to load the 3D gray value image that you can turn to every direction now. Here you see the resolution and the size of the scan. It's 1400 times 1400 times 200. And here's also the resolution. When you now go to the new window, the segmentation and labeling window that is here, you have two small windows inside. The first window is the image processing window, where we are now going to crop the data. For that we have a smaller time to calculate. We're going to crop that to these values. I checked them before. The NZ direction we're not going to crop that because it's the thickness of the cathode. Now we go and apply, and now we see that the scan is much smaller than before, and we can make the view mode a little bit different, so it's a little bit bigger. So 100%, I think 50% is enough. And now we go to the segmentation and labeling window and go to global thresholding. Here is the first thing we're going to do is to change the name of the result file, because the name of the PNGs, we don't need them, and it's a little bit confusing. Here with segmentation, the gray value is going to be assigned to a color, and the color is assigned to special voxels, and those voxels are giving a material ID. And here the Otsu filter has already done its work. You can check the visibility to make it easier or worse to see. You can also make that manual, where you can here change the threshold if you don't like the result of the automatic segmentation. For this scan, the automatic is doing a little bit better job, so we'll keep the, it's wrong here, I was here. We keep the automatic version and we click on create segmentation. Now a new window is going to open. That's the result viewer, where you can see the results of the step you did. Here's the domain, the voxel length, and you now click on load structure and you can close the segmentation window and you can see your structure and the gray value that is overlaid. Now you can turn the scan. You can also go on reset view. For that you have the same view. Now we're going to delete or to discharge the gray value image, because now it's two structures overlaid. We have structure and the image, and the image we don't need anymore, so we're going to discharge it, and we now have the voxelized structure of our material that we can also render in a different way. That's the box renderer, where you can see the voxels. And now we're going to make the smooth renderer, because it's easier for our eyes to see this, or to assign that to something round. It's more natural. The next step is to check the color code. It's a little bit red. We're going to make it in a gray. And the next color we already assigned to red. That will be the binder phase. When we did this, we check the result of the segmentation, and we go to the material parameters. That has a field. Here you can select the constituent materials. We have a pore that will be filled with the electrolyte. Can click OK. And we have the solid, that will be the material NMC 383. And we can assign those. Here's also a new overview window. You can open that, and it's a report for the material that we assigned to, for example, ID 01. I can close this here, and I will run this. Now I assigned those materials and check the result. It's here. Can go like this. We know, I already told you that we have to assign the binder phase that we assign to the color red. To do this, we go on, not on module, we go on grain find. It's under analyze, and we open the module grain find. Here we have the identify binder artificial intelligence. Take care, we are not going to run it. It will need something about 50 minutes. I show you how to do it, and then we will open the result file and open the structure. That will make it a little bit easier. So when you have the identify binder, you click on edit, and you see that the window is opening. You look at the identification mode, use current structure. Here you have all solid materials. Here you see the color that we are going to use for this, and we already assigned this to red. Periodicity, we just let everything like this. We click on OK, and we don't click on run. We will not click on run. We'll open the result file. To do so, you go to the analysis folder. It's 02, the handout folder, and you check the GeoDict result file, identify binder, and you drag and draw this file into your GeoDict, and then you see that the identify binder result file is going to open. It says that there's 4.0842% binder in the structure. It gives you a binder distribution map, and you have also the binder visualization where you can load the structure with the binder. You click on that, you wait a second, and then you see here the structure together with the binder. And you can see the binder distribution. The next thing we're going to analyze is the pore size distribution. And for this one, I want to present you two different kinds or two different methods that GeoDict can calculate. The first thing is the granulometry, where the pore body, so the volume of the pore, is analyzed. For this, GeoDict fits spheres into the pore and the voxels become the color of the largest fitting sphere at this place. The porosimetry on the right side is imitating the experiment with mercury that you can do also in the lab. Here, the algorithm is fitting the pore with small spheres. So one time we get the real volume of the pore, and on the other time we get the results that we can directly compare with the experiment. On the left side, the granulometry is a size that we cannot get in experiments. When we go back on GeoDict, we can calculate the granulometry while going to Analyze and to PoreDict. That's the module here. Now the PoreDict module is going to open, and we choose the first experiment, the granulometry. We click it and we go on Edit. We let all the parameters like it. Just make a check mark to write pore size distribution as GSD file. Then we click OK and we click on Run, and we wait until the pore size is calculated. It needs maybe some seconds, but this is okay. So now the result view is opening, where we can see the diameters of the pores. We can see the plots where the pore diameter is plotted against the volume fraction. We also have the map where we have the data in a table. And if you want to see the volume field, or we load the GSD file, we click here, we have all this, we click on OK, we wait a second, we close it here, and then we have the volume field together with the structure. To analyze the pore size, we only look to the volume field and not on the structure. So we uncheck the structure, and we also uncheck that here those two are unchecked, and then we can play a little bit around with the volume field and the pore size biggest, and then you see that just the biggest pores are well distributed in the volume field. So now we did the granulometry experiment, and we unchecked the volume field and checked the structure again. And now we do the porosimetry experiment. We do the same than before. We go on Edit. We make the check mark to write pore size distribution. The wetting part is okay. Here we see the material parameters. We can keep all those values on the default. Click on OK, and then we click on Run and wait until the GeoDict result file is going to open. It will need as much as time for the granulometry. So we wait those seconds, and then we will have the view, and then we can also compare the data. We see that the porosimetry result view is going to open. It looks quite similar for the first part than the result view for the granulometry. We have also the minimal grain diameter, the maximal diameter, and the volume fraction. And also for the porosimetry, we can And laser plots where the pore throat diameter is plotted against the volume fraction. And also here we have the result map with the data in the form of a table. And also here we can click on pore size visualization and on load GSD. And we click on OK and we load it. Now it's loaded in the back, and I want to show you how to compare result files. Now we have those both. We can mark both of them and then go on the result map, on the plots, for example. Here, results, plots, make the window a little bit bigger. And here you can analyze how both of them distinguish on their view, and you can also plot them into one diagram when you click on combine results. Here it's asking those. You click on combine results, and now you got a plot where both diagrams are plotted together. And this function makes the results easier to compare. After doing the import, the segmentation, and also the first analysis on our sample, I think it's time to have a 10 minutes break. If you have questions, just ask. I will be here around, and we'll see you in 10 minutes back.